Hello, and welcome back to another lesson in Math 1106, Math for Business Precalculus. My name is John Adamski, and this is week 7. Our topic this week is graphs of functions. So we'll begin by introducing the xy plane and the Cartesian coordinate system for plotting points in the plane. We'll move on from that to graphs of equations. Whenever you write down an equation involving two variables, x and y, that generates a graph, a visual representation of the solutions to that equation. And we'll spend the rest of the time focusing on graphs of this particular equation, y equals f of x. We call that the graph of the function f. And then once we are comfortable with how graphs are generated and what information they're showing us, we'll use that to solve equations using the graph, solve inequalities using a graph, and then we'll also talk about, if you do not see the graph of a function, can you still tell me what its x and y intercepts are, where the graph crosses the x and y axis? You can find those algebraically by solving equations. So that's our agenda, and let's get to it. Now, if you have just one number, there is a way to visualize that number by putting it in its place on a single number line. The big idea behind today's lesson is that if you have two numbers, say a comma b, and the order matters, so there is a first number and a second number, there is a way to visualize a pair of numbers like this too. And the big idea comes from the mathematician René Descartes, who was born around the year 1600. So this is an old idea that we take for granted today, but it was new at one time. The idea is that if you have a pair of numbers, give yourself a pair of number lines. For convenience, let's just put them at 90-degree angles from each other. And let's have them intersect at their common zero. So this is the x number line. It's just a regular number line. This is another number line, but I'm labeling it with the letter y to distinguish it. And this point right here is both 0 on the x-axis and 0 on the y-axis. With this setup, what you've given yourself now is a coordinate system for determining the coordinates of any point in this plane. This plane is now called the Cartesian plane, named after René Descartes, or also called the xy plane. And so let's take a look over here. Example 1, I have some points in the plane, and I want to determine their coordinates. Now, this is very similar to determining the coordinates of a point on Earth, where you talk about longitude and latitude. You measure how far east and west a point is from a certain point, called the prime meridian. You measure how far north or south that point is, measured from the equator. Well, you know, the y-axis here is playing the role of the prime meridian. You can be east or west of that line. The role of the equator is being played by the x-axis. And so anyway, let's just start here with this point. Okay? So if I have to determine its x and y coordinates, its first and second coordinate. The first coordinate is your horizontal coordinate. So I'm ignoring the height of this point. I just want to know left and right-wise, where is this point? And so I can determine that by dropping a vertical line from this point to the x-axis. And where it meets the x-axis, where that vertical line meets the x-axis, is of course at 1. And that is the x-coordinate, or the first coordinate of that point. The second coordinate is its height. I can find that by drawing a horizontal line from this point to the y-axis. That would be 1, 2, 3. That would be 4. So 1, 4 is the label for this point. Those are its coordinates. Its x and y coordinates are 1 and 4. Okay? For this one, let's see. This point lies 2 spaces to the left of the origin and 1 space above the origin. All of our positions are measured from the origin. The origin is the center of this plane. And so since it's 2 to the left, it gets a -2. And since it's 1 up, it gets a +1 for the x and y coordinates, the horizontal and vertical coordinates. Okay? So you have to understand that in terms of left and right, In terms of in terms of the horizontal position, moving to the right is the positive direction, and moving to the left is the negative direction. That's the way the x-axis is oriented. And vertically, up is the positive direction, and down is the negative direction. Okay? So that's why this has a negative x coordinate. Moving on, this point over here, let's see, it's 3 units to the left of the origin, and it's 3 units below the origin. So its coordinates are -3, -3. This point over here is 2 units to the right of the origin, so its first coordinate is 2, and it's 2 units below the origin, so its second coordinate is -2. Okay? And then we have, let's go to this point over here. Its x coordinate is 3. Its y coordinate is 2. And then we have these 2 points here that are actually on the axes themselves. Okay, so this point lies 1 unit to the left of the origin, so its first coordinate is -1. And since it's on the x-axis, it doesn't have a height above or below the x-axis. It's on the x-axis. But you know, if I draw a line from this point to the y-axis, it intersects the y-axis at 0. Its y coordinate is 0. And similarly, this point, which is neither left nor right of the origin, has x coordinate 0, and its y coordinate is -1. Okay? Every point on the x-axis has y coordinate 0. Every point on the y-axis has x coordinate 0. That's easy to see. Let's work in the opposite direction. Now I want to start with coordinates and determine where those points are in the plane. Okay? And this is sort of highlighting the big idea that René Descartes had, which was when you have just pairs of numbers, you know, you have a visual for that. If you know that when x equals -1, y equals 2, there's a way to picture that. And so that's what we're developing here. We're drawing the picture that these numbers are describing. So for this first one, let's see, we have -1, 2. So I'm going to move left and right until I'm in line with -1. That puts me here. And then I'm going to move up and down until I'm in line with 2. That puts me at this height. So I need to be right here. That's where the point A is. The point B, 1, -3. So I'm going to move to the right 1, and I'm going to move down 3. Okay? Taking the negative sign tells me to move down. So this is 1, -3. For this one, -2, -2, I'm going to move in the left direction for -2 and down for -2. Okay, so here I am at -2, -2. For 2, 0, I'm going to move 2 units to the right, but I'm going to stay on the x-axis. If the y coordinate is 0, you are on the x-axis. This one has x coordinate 0, so I'm not going to move left or right at all. I'm just going to move up 3 units from the origin. And that puts me here at E. Okay, so these are those points plotted. It might be worth pointing out that the x and y axes themselves divide the plane into 4 quadrants is the word. We have quadrant 1 here, where x is positive and y is also positive. And then from here we just count in a counterclockwise fashion. This is quadrant 2, where x is negative but y is positive. This is quadrant 3, where x is negative and y is negative. And over here is quadrant 4, where x is positive but y is negative. Okay? The axes themselves, it's a toss-up whether you want to include this x-axis in any of the quadrants or whether you don't. I'm going to say no, because I've defined them to be only when the x and y coordinates are either positive or negative, puts you in one of these 4 quadrants. Okay? Now that we know how to plot points in the Cartesian plane, we're ready to talk about what the graph of an equation is. And this is really the genius of what René Descartes invented when he invented the Cartesian plane. This is what he had in mind. The graph of an equation with 2 variables, x, y, is the set of all points x, y with coordinates that satisfy the equation. So for example, here's an equation involving x and y. This is what I'm talking about when I say an equation with two variables x and y. This is a great example. Okay? I just made this up, I just wrote this down, but it's certainly an equation, and it does involve two variables x and y, and only two variables. Now, there are certain values of x and y that make this equation true, and there are certain values of x and y that make this equation false. Every point in the plane is either one or the other. It either causes this to be true or false. The graph of this equation would be the set of all the points that make the equation true. And what's the brilliance of René Descartes, I'll stop toting the brilliance of René Descartes in just a second, but while studying these equations and what the solutions of equations like this would be is interesting in its own, he showed that this actually creates a picture. And the picture can have patterns involving symmetry that can shed light on the solution and a better understanding of the solution. Now this is a tough one. I just made it up. It is a fun thing to do, though, to go to Desmos.com and click on the graphing calculator and just type in any random equation you can come up with involving x and y and see what pretty picture it displays. Or maybe it's not pretty, maybe it's ugly. But what the graph looks like. And then how changing any of these numbers or any of the signs of any of these operations would change the corresponding picture. It's a fun thing to do. One that we can actually do by hand, just to get a little bit of experience with this, is this equation right here, x squared plus y squared equals 25. This one is simple enough that I can think of some solutions off the top of my head. For example, whether if x is 5 and y is 0, this would say that 5 squared plus 0 squared equals 25, which is true. And it would also be true if x were negative 5 and y were 0. So since this pair of values, 5, 0, causes the equation to be true, 5, 0 is on the graph of the equation. It's going to get a point plotted representing that solution. So this solution is represented by that point. Of course, there are two here. I said 5, 0 and negative 5, 0. So here's that other solution. So the solutions to the equation are visualized as points in the plane. And we can keep going. There's, of course, two other easy ones. When x is 0 and y is either positive 5 or negative 5, 0 squared plus 5 squared equals 25. So 0, 5 is a solution. 0 plus negative 5 squared is also 25. So 0, negative 5 is also a solution. And it's not hard to see that there are many others. X could be plus or minus 3. Y could be plus or minus 4. That would look like this. Here's 3 comma 4. Here's negative 3 comma 4. Here's negative 3, negative 4. And here's positive 3, negative 4. Actually, I think I have this in the wrong spot. That should be negative 3, negative 4. OK? Actually, this one's also in the wrong spot. Negative 3, positive 4. Sorry. OK? And let's see. If x is plus or minus 4 and y is plus or minus 3, here's 4 comma 3. Here's negative 4 comma 3. Here's negative 4, negative 3. And here's 4, negative 3. OK? Those are the only easy solutions that I have, but it's easy to write down some other ones that are maybe not so obvious. But this number squared plus that number squared also equals 25, regardless of whether I'm taking plus or minus here. OK? So there are lots of solutions to the equation, and you could plot them in the plane and sort of try and get a better understanding of what is it that all of the solutions have in common. And in this case, while it might not be obvious from what I've drawn, it turns out that all of the solutions lie on a circle. So this circle that I'm drawing is made up of points. There are points here, 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 here. It's made up of points. Every one of those points has an x and a y coordinate, and every one of those x and y coordinates satisfies this equation. So suddenly this equation, this very dry algebraic equation, has a picture, a circle, associated with it. And this idea that you can, once you have a solution, you can switch its x and y coordinates, make them positive or negative, shows itself by all of the symmetry that this shape has. When you switch the x and y coordinates, you reflect the circle. When you negate the x and y coordinates, you reflect the circle. And the circle has so many lines of symmetry that the picture conveys that algebraic fact about solutions at a glance. And so this is the kind of insight that a graph can provide. And so this is why we focus so much on graphs in mathematics, because at a glance they convey a lot of information and a lot of important information about the equation that you're looking at. Well, now that we know how to plot points and we know that the graph of an equation is just the set of all points that satisfy the equation, we can finally talk about the graph of a function. Here's the definition. Given a function, f of x, the graph of your function is the graph of the equation y equals f of x. That's it. So the graph of a function is the graph of an equation. It's the graph specifically of this equation, y equals f of x. In other words, the graph of f is the set of all points such that y equals f of x. The set of all points in the plane whose y coordinate is f of its x coordinate. And that's sort of reiterated right here. In other words, it's the set of all points x comma f of x. Okay? You could kind of stop the sentence right there, but this isn't going to exist when x is not in the domain. You can't plug numbers not in the domain of f into f. So it's the set of all points x comma f of x such that x is in the domain of f. Okay? But it's just the graph of the equation y equals f of x. That's it. So, for example, it says here, use the graph of f to the left to determine some values of the function. Okay? So what you're looking at here is the graph of y equals f of x. Every point that you point to, okay, has an x and a y coordinate, and it must be that the y coordinate is f of the x coordinate. So this asks, what's f of negative 2? And so all we're going to do is we're going to find the point on this graph whose x coordinate is negative 2. Now, x equals negative 2 is here. All of these points have x coordinate negative 2, but only one of those points is on the graph, and it's right here. Okay, so I went over along the x-axis and I found negative 2 on the x-axis. And now what's y? Well, I go up and down, I scan visually up and down until I come to the graph, and the graph shows me that this point with x coordinate negative 2 and y coordinate 2 is on the graph. So f of negative 2 is 2. And the reason is that negative 2, 2 is on the graph. There is a point on the graph with x coordinate negative 2 and only 1. And the y coordinate of that point happens to be 2. Okay? So the x coordinate of this point is telling me the input, the x coordinate. And the y coordinate of this point is telling me the output, y. Okay? What's f of 0? Well, I scan the x-axis until I find 0. There it is. I scan up and down until I find where the graph is, and it's right here. This is the point 0, negative 3. And it's on the graph. So 0, negative 3 satisfies the equation y equals f of x. That says that negative 3 equals f of 0. Okay? So f of 0 is negative 3 because 0, negative 3 is on the graph of f. That's it. What about f of 3? What would f of 3 be? Well, maybe you can start to get the idea here. This is the point 3, 1, and it's on the graph. So that means that 1 is f of 3. f of 3 is 1. And f of 5, I come over here until x equals 5. I scan vertically to find the point on the graph whose x coordinate is 5. It's this point where the y coordinate is 3. Since y equals f of x, 3 equals f of 5. f of 5 is 3. And that's it. That's how you read off the values of a graph. Okay, so what else can we do with the graph of a function? Not only can we read off values of the function, but we can solve simple equations involving our function. For example, This question says to use the graph of f, shown here to the left, to find all solutions to, and we have an equation. This says f of x equals 1. Now, I don't know what f of x is. The only thing I have to go off of is what its graph looks like. What is this saying? You have a function f, and the input is x. The input is unknown, but the output is 1. So this is asking for what inputs into f does f output 1? Okay? And looking at its graph, we know that the role of inputs are the x coordinates on the graph, and the role of outputs are the y coordinates. So all I need to do is scan this graph and try and find points on the graph where the y coordinate is 1. Remember that what you're looking at here is the graph of the equation y equals f of x. Maybe I'll just reiterate that. Y equals f of x. So when they tell me that f of x equals 1, I know that y equals 1. I want to know where are the points on this graph where the y coordinate is 1. And I see a few. I'm sort of just scanning this. I'm trying to find all the points on the graph where the y coordinate is 1. Now, I just drew the horizontal line representing all of the points whose y coordinate is 1, and it shows me that there are a few points on this graph where the y coordinate is 1. I'm just highlighting them right now. Okay, it looks like there are 4 points on this graph where the y coordinate is 1. So this tells me that f of negative 5, this is the point negative 5, 1. Okay, so when x is negative 5, y is 1. That's one solution. X equals negative 5. Another one would be 0 because 0, 1 is on this graph. Another one is 2, 1. Another one is 4, 1. So reading off what these x values are that produce outputs equal to 1, I think I've got it here. I think it's negative 5, 0, 2, and 4. Okay? Again, that comes from the fact that negative 5, 1, 0, 1, 2, 1, and 4, 1 are all on my graph. So all of those x values, when input into f, produce the same output of 1. The question here is quite similar. It says, find all the solutions to f of x equals negative 2. So now I want to come down to my graph. I want to know what are all the values of x on this graph where the y coordinate is 2. And if I just scan this graph, I see that there are a few points. Looks like there are maybe 4 points on this graph where the y coordinate is negative 2. Okay? And so, again, all these points have the same y coordinate, negative 2. I want to know what are their x coordinates. Okay? For example, this point down here is negative 3 comma negative 2. That's this point right here. And that tells me that f of negative 3 is negative 2. So that's a solution. Okay? I'll just go ahead and reveal all the solutions. Negative 3 is one of them. This point over here is negative 2, negative 2. When x is negative 2, y is also negative 2. Okay? So negative 2 is another solution. This is the point 3, negative 2 over here. 3, negative 2. F of 3 is negative 2. So 3 is another solution. This one, I kind of have to guess. Sometimes this happens with graphs. I tried to make all of the points line up nicely with the grid. But sometimes you just have to guess because graphs are not super precise. And neither is our vision. So I have to ask myself, what do I think the x coordinate of that point is? Well, it's somewhere between 3 and 4. I'm estimating it to be 3.5. Okay, so I'm saying this is the point 3.5 comma negative 2. So f of 3.5 is negative 2. So 3.5 is a solution to this equation. Okay? Not so bad once you get the hang of it. Now, you may know this from high school, but there are features of a graph called x and y-intercepts. The x-intercept of the graph is where the graph intersects the x-axis. Okay? And notice that whenever you're on the x-axis, wherever you are on the x-axis, your y coordinates are 0. So this graph has a couple x-intercepts. There's one here, 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 and here. None of those are lining up with the grid precisely, so it's a little bit hard to tell what those x-intercepts are. But I made a guess and said that those x-intercepts were negative 4.8, negative 0.5, 2.3, and 3.9. That's what I said the x-intercepts are. Now, I'm going to go one step further and say the x-intercepts are actually these points. It's those same numbers, but these are just numbers. X-intercepts are points in the plane. They are points on the graph. And as a point, it has both an x and a y coordinate. Now, they're on the x-axis, so their height is 0. Their y-coordinates are all 0. These are their x-coordinates. So what are the x-intercepts? The x-intercepts are these 4 points with both x and y coordinates. Similarly, we can talk about y-intercepts. Now, when you're talking about the graph of an equation, the graph of an equation can have any number of y-intercepts, but the graph of a function can only have one y-intercept. That's because, you know, this graph you see only has one y-intercept, and that's because f of 0 is 1, and f of 0 is not any other number. So there cannot be any other points on this plane on this graph with x coordinate 0. If there were, then f of 0 would be 2 different numbers, and that's not how functions work. So the graph of a function can only have one y-intercept. And you find it by setting x equal to 0 and seeing what the function outputs. So the y-coordinate is f of 0. The x-coordinate is 0. On my graph, again, 0, 1 is on my graph. So the y-intercept is 1, and that's what I wrote here. The y-intercept is 0, 1. That is the point that is the y-intercept. Let's look at another example and go one step further and start solving some inequalities using a graph. So again, I'm not telling you what the function f is. All I'm doing is showing you its graph, which does convey a lot of information about the function, enough for you to answer the following questions. So part A says, use the graph of f to find the solutions to f of x equals 0. For what values of x does f output 0? Well, the outputs of f are the y-coordinates on its graph. So I'm looking for points on the graph where the y-coordinate is 0. Well, those are the x-intercepts, aren't they? So there's an x-intercept here at -4, -1, 2, and 3. So those are my solutions. -4, -1, 2, and 3. OK, simple enough. Maybe let's highlight those on the graph, those x-intercepts. -4, -1, 2, and 3. All right, cool. Now what about this one? It says the solutions to f of x is greater than or equal to 0. Well, I already know when it's equal to 0, so those are going to be included in this solution, in the solution to this inequality. But where is the function outputting numbers bigger than 0? Where are the points on the graph where the y-coordinate is positive? That's what this is saying. Remember, y equals f of x. So we're looking for where is the y-coordinate greater than or equal to 0. Well, that means where is the graph above the x-axis or on the x-axis? And so that's going to be everything to the left of -4. I'm just going to reveal my answer right now. It's going to be everything to the left of -4. I'm making a bit of an assumption, which is that this graph continues to go up, 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 up as you move to the left. I don't actually see that. The graph terminates at a certain point, but I'm assuming that the graph continues to go up forever as you move to the left. So that the graph stays above the x-axis as x goes all the way to -infinity. Okay, so all the way from -infinity to -4, the graph is above the x-axis or on the x-axis. But between -4 and -1, it's not, f of x is not greater than or equal to 0. The graph goes below the x-axis, so the y-coordinates are negative. That means that f of x is negative for these values of x between -4 and -1. But between -1 and 2, f of x, the y-coordinates of the graph, are once again positive. So between -1 and 2, it's positive. And between 3 and infinity, it's also positive. I'm including all of these endpoints except for the infinite endpoints, because at those finite endpoints, the graph is on the x-axis and f of x is equal to 0, which does satisfy this. In the follow-up question, I say, what are the solutions to f of x strictly greater than 0? It's almost the same answer, but now I want to remove those endpoints. So -4, -1, 2, and 3 are no longer solutions because at those points f of x is equal to 0, not greater than 0. Now, in part C, it says, what are the solutions to where D, the solutions to f of x less than or equal to 0? Well, we already know when it's equal to 0, and when is it negative? Between -4 and -1, and between 2 and 3. You see, I'm just looking for where the graph dips down below the x-axis. And importantly, I'm focusing on the x coordinates for which it does that. It should be clear that the solutions, what we're solving for here, are the x values. So I know that it dips down all the way to like -5. It dips down all the way to like -1/2. If you are looking at the y coordinates, you can see that. But all I want to care about is for what values of x are the outputs of my function negative. I don't care what those outputs are, except that they're negative. And the inputs that cause the output to be negative are between -4 and -1, and between 2 and 3. So those are my solutions. And when I ask what are the solutions to f of x strictly less than 0, it's almost the same thing, but I'm going to remove those endpoints where the graph is on the x-axis. Now we're only between -4 and -1, not equal to -4 and -1. For those values of x, f of x is negative. And for x strictly between 2 and 3, f of x is negative. And again, I can see that because the graph is below the x-axis. That's it. All right, here's another example, more or less doing the same thing. I have a new function here. This is the graph of f. This is all I have to go on to answer the following questions. Can I find the solutions to f of x equals 4? For what values of x does f of x equal 4? Well, I'm going to look at my graph here and try and find points on the graph where the y coordinate is 4. So I see one here, 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 and here. It looks like there are 4 points on the graph where the y coordinate is equal to 4. Okay, I'm just kind of highlighting how I'm finding those. I'm starting with the y coordinate equal to 4, and I'm figuring out what are the x coordinates of the points on the what are the x coordinates of the points on the graph where the y coordinate is 4. Okay, and there are 4 of them, and I think I have them listed over here. They are at -5, -2. This is -5, -2, 0, and 4. Okay, those are the x coordinates of those points. The y coordinates are 4. And what are the solutions to f of x greater than 4? Well, this is just asking when is the graph above that line that I just drew, that line y equals 4. Well, it's all the points from -∞ to -5, from -2 to 0, and from 4 to infinity. Again, I'm making a few assumptions there. I'm assuming that the graph continues to go up and to the left and up and to the right. That's how I'm putting -∞ and infinity into the mix. And where are the solutions? What are the solutions to f of x less than 4? Where is f of x less than 4? Well, it's everywhere else. It's between -5 and -2, and between 0 and 3, right? Between -5 and 2, between 0 and, oh, sorry, I misspoke, between 0 and 4. Okay, and what are the solutions to f of x equals 2? All right, this is a little bit different. F of x equals 2. Well, all the points where the y coordinate is 2 lie on this line that I just drew, more or less, right about there, right? And so there are a couple points on the graph where the y coordinate is 2. Looks like there are 1, 2, 3, 4 of them, okay? And what are the x coordinates of those points? I know the y coordinates are 2. What are the x coordinates? Looks like the x coordinates are -4 and -3, 1 and 3. So I think those are my solutions to this equation. And then, of course, I asked the same follow-up questions. Where is f of x greater than 2? And where is f of x less than 2? This is asking you, where is the graph above this green line? And where is this graph below that green line? And these are intervals for x, okay? We're talking about what values of x cause the output to be greater than 2. And we can see it's everything from -∞ up to -4. and then everything from -3 over to 1, and then everything from 3 up to infinity. And so that's described by these intervals right here. They're open intervals. They don't include their endpoints because at their endpoints f of x is equal to 2. I don't want to include that. And when is f of x less than 2? Well, essentially everywhere else. It's less than 2 when the graph goes below this green line. So that's between -4 and -3, and between 1 and 3. And so those are going to be that's going to be my answer. It's these open intervals, endpoints not included, because at the endpoints the function is equal to 2. And so that's how this goes. And to wrap things up, let's answer a question about the graph of a function without knowing what the graph looks like. This time I'm given a function algebraically. It tells me f of x is equal to this polynomial function. And can you find the x and y intercepts of the graph? Of the function has a graph. It's the graph of the equation y equals f of x. But I'm asking, without seeing the graph, can you answer this question about the intercepts? The answer is yes. To find the x-intercepts, okay, we're going to set our function equal to 0. So we're going to set f of x equals 0, and we're going to solve for x. Okay, so for us, this equation looks like this. 2x squared plus 4x minus 70 equals 0. And I have to factor the left-hand side. I'm going to pull out the greatest common factor of 2. So I have 2 times x squared plus 2x minus 35 equals 0. And I'm going to factor a little bit further. I can factor this quadratic polynomial here into, let's see, I need to find 2 numbers that multiply to be -35 and add up to 2. I think 7 and -5 are the numbers that are going to do that. And so I can see what my solutions are right away. Either x plus 7 equals 0 or x minus 5 equals 0. And so my solutions are x equals -7 and x equals +5. Therefore, my x-intercepts, it's bad form to just circle this and say that that's my final answer. The question was, what are the x-intercepts? And the x-intercepts are points in the plane. These are the x-coordinates, but you have to show that you know that the y-coordinates are 0. So these are the x-intercepts. They are points in the plane. They have both x and y coordinates. The y coordinates are 0. Finding the y-intercept, there's only one y-intercept for the graph of a function, and it's very easy. We're just going to evaluate f of 0. Okay, in this case, that's pretty easy, and it usually is. 2 times 0 squared plus 4 times 0, that's all just 0, minus 70. So f of 0 is minus 70. Okay, so that's my y-intercept. You do have to remember that when it comes to points along the y-axis, okay, this one happens to be -70. As far as a point in the plane goes, it does have an x-coordinate. The x-coordinate is 0, right? 0, and the y-coordinate is -70. So the y-intercept is the point 0, -70. And, you know, the x-intercepts we said were -7 and +5. So this graph could look something like this. I have 3 points on its graph precisely plotted. It's supposed to go through that point. What the rest of the graph looks like, who knows? Maybe you know that the graph of a quadratic polynomial is a parabola. So it does have this shape, and it does go through these 3 points. So now you have some idea of what the graph looks like. But this is just a sketch. It's not very precise, and it shouldn't be used to answer really many questions at all. But this is how you find the x and y intercepts of the function algebraically. There are some trickier examples in the practice problems, but we've already gone over how to solve equations. So as long as you're able to set up the equations that need to be solved and plug in the numbers that need to be plugged in, you should be able to find the x and y intercepts no problem.